Okay, this is an additional scenario on confidence intervals for the one sample T distribution. So insurance companies track life expectancy information to assist in determining the cost of life insurance policies. The insurance company knows that last year, the life expectancy of its policyholders was 77 years. They want to know if their clients this year have a longer life expectancy on average. This is what we're looking for. That's what they're interested in. So the company randomly samples, and that's nice to know a random sample, because remember your data is no good unless it's randomly selected, or might not be good if it's not randomly selected. Some of the recently paid policies to see if the mean, in other words, we're looking for an average, the life expectancy of the policy holders has increased. The insurance company will only change their premium structure if there's evidence that people who buy their policies are living longer than before. Does this sample indicate that the insurance company should change its premium because life expectancy is now different? Calculate a 90% confidence interval. All right. Now, they ask this question. We need to make sure that we don't ignore this. Does this sample indicate that the insurance company should change its premium? So ultimately, we're going to have to come back and answer this. Okay, so we're going to need to calculate a 90% confidence interval, and they've given us a string of data. We need to put all this data into stat edit in L1, which I've already done. So if I go to stat edit, I now have all my data listed in L1. Great. But we're doing a confidence interval. And according to our recipe, the very first thing we have to do is define the parameter, the mu or the mean, in context. So in this case, let mu equal the true population mean of policyholders' life expectancy in years. This part should never change when we're doing a one sample T, true population mean. And then this one is the context provided by the problem. You always have to define it in context. So like mu equal the true population mean of life expectancy or policyholder life expectancy. The second thing we need to do is we need to write our conditions out. Okay, and the first condition is random sample, and they told us it was random, so we're going to say that it was a random sample, and that was given. The next one is N is less than 10% of the population, and remember, this kind of goes back to independence, and because we are sampling without replacement, we really aren't independent. So the question is, well, how much do we want to sample before we have to do a correction? Well, basically, if our sample size is less than 10% of the population, you're good to go. So in this case, we've written random sample, and that was given because they told us that up in here. Our sample size, I counted these up, and there was 20 and divided by 0.1. And you have a choice. You can either do that or 20 times 10, either way. And basically, we're going to assume they didn't give us the population size, but we're going to assume that they have at least 200 policyholders. So as long as they have at least 200 policyholders, our sample of 20 is less than 10% of the total population. All right, so that's probably a pretty good assumption. Okay, in this case, the next thing we need to check is what I call the normality condition. Extremely important condition. And there's a couple ways to test it. One, if the underlying population is normal, we're good to go. If our sample size is 30 or larger, we're good to go. Well, they didn't tell us the underlying distribution, so we don't know if it's normal. Our sample size was 20, so it's not greater. So if they gave us data and it's less than 30, we're going to have to check it using a graphical mean. I recommend using a box plot because box plots are so easy to draw. Okay, so here's the way you do that. We have our data. We've already entered it into the calculator. I'm going to go to y equals and make sure I don't have anything in there, and I don't. And then I'm going to go to second stat plot. I want all of them turned off except for the first one. arrow over to the left. Make sure I select the box plot indicating outliers. My X list is L1, and I have no frequency this time. It's just that list. So my frequency is 1. I just needed it to occur one time. Then I press zoom 9. Now, every now and then calculators will mess up and do that. If you hit clear and then press zoom 9, it'll pop up. And when I look at that, it's not perfectly symmetric, but it's pretty close. And so we're looking for something that's reasonably symmetric. And remember, we can use the trace feature to get the actual points, which might help you with your graph. You do have to draw this. So when I look at it, it's like, well, my lower part of the graph was at 70. This is my minimum value in this case. My Q1 was at 75.5, and that's Q1. 79 happened to be my median. $82 is Q3. Then I have a maximum value of 86. So you have a choice, and either you can label the major points like I just did, or you can draw the scale. Regardless, you need to make sure that you label what it is. So here's what I'm going to say. The box plot is reasonably symmetric with no outliers. The distribution appears to be approximately normal. This is a very key word. Make sure you say approximately, reasonably normal. At this point, we're ready to start working with the actual calculations. And by the way, what we've done so far typically gets you 1 point on the AP exam in our grading rubric. All right. So the next thing it asks for, we're going to need to do our computation. So I write down my formula, which is X bar plus or minus T star, the sample standard deviation divided by the root of n. In this particular case, I can go to stat calc, slow that down, stat calc, one variable statistics, enter. And my X bar is 78.6. Plus or minus, I'm going to leave a space for the T star. I'll come back and get that in just a moment. My standard deviation is S of X, and we'll talk about that in just a second. I just write it down. 4.4768. And the S of X represents your standard deviation of the sample. This is standard deviation of the population. If we're entering data, it's almost always going to be from the sample. And in fact, they told us this was a set of sample data. So if it's a sample data, we're going to use S of X. If we have the entire population, we'll use this. Okay, but that's not going to be very typical when we're entering data. My sample size is 20, so we're going to take the square root of 20. And at this point, the only thing that I'm missing is my T star. So how do I get that? Well, I'm going to go to second vars, inverse T, parenthesis. I'm going to clear that out. For my area, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. And my degrees of freedom is 20 minus 1, because my sample size is 20, so n minus 1. And it's going to take a moment while it calculates it out, and I get 1.7291. And so that right there represents my T star. Notice I made it positive, it makes it much easier. And I just want to draw this out there, although it's not required. This might help to people with some understanding. All right, so we're doing 90% confidence interval. And so what we're saying is we're 90% sure or 90% confident that that our interval will capture the true population mean. That it's going to lie somewhere between this lower value and this upper value. We just calculated a t-statistic of negative 1.729 and an upper of 1.7291, because remember the t-distribution is centered on 0. And this is my x bar, this is my mean. And now we're actually going to go and calculate the interval. Well, I can do this by mathematically, by algebra, or the calculator is very, very friendly. Stat test number 8, which is t-interval. In this case, I'm using data, so data needs to be highlighted. My data list happens to be an L1. My frequency is 1, because I only have the one list. And my confidence level is 0.90. Make sure you're using a decimal. And when I do that, I end up getting a lower bound of 76.869. There's the X bar that we calculated. And here's the standard deviation of the sample that we have. So we have a lower bound of 76.869 from the calculator. And then we have an upper bound of 80.331. So for their actually what we have, these are our t star values. What we actually have is 76.869. Our mean, our X bar, is 78.6. And our upper bound is 80.331. Now we will note, so we're 90% sure that the true population mean will lie somewhere in here. Now there's a 10% chance it doesn't. All right, there's a 10% chance it doesn't. Now, really quickly, I want to talk about this. This is all confidence intervals are two-tailed tests. In other words, I have area in the tails. That area happens to be known as alpha. Alpha is just the area in the tails, which is 1 minus 0.90, is 0.10. So alpha in this case is 0.10. And this is alpha over 2, which is 0.05. And this is 0.05. Put these together, sum for that. Now we'll go into more than that in the hypothesis testing, but just wanted to make sure that we know what alpha is, or that we see alpha right now. All right. And alpha kind of is a rejection zone. So if we end up in alpha, we tend to say, hey, we're going to ignore what happened. All right, so this computational part that we just did is worth another point. And then our conclusion is typically another point, which in this case, we are 90% confident the true population mean life expectancy for policyholders lies within the interval. All right. This will change based on our confidence level, but we are blank confident the true population mean. This part, other than that, this part should not change ever. All right, true population mean, and then this is our context. And really our context is just what we had up here. Life expectancy of policyholders, life expectancy for policyholders, and then we need to say that it lies within our intervals. So this is interpreting our interval. And if you were to look at the recipe sheet, that's number 11, the conclusion, interpreting the interval. And then they also may ask us to explain the meaning of the confidence level, which in this case would say, in repeated sampling, or if we did this over and over again, or if we took all possible combinations of size 20, we would expect that this method will capture the true population mean of life expectancy, once again, in context, 90% of the time. And again, we're just following the template right there, all right, which is number 12. Now, one thing I have to say is this is worth one other point. But there's one thing that is skipped, or I have not done. It says, does this sample indicate that the insurance company should charge its premiums? I still haven't answered that question. Well, they want to know whether or not it's changed. Is it now different? Well, when I look at my interval, 77 lies within that interval. And because 77 lies within the interval, we're going to say because 77 lies within the interval, there is not enough evidence to say that the life expectancy changed. All right, 77 is contained in the interval, so it doesn't look like the life expectancy has changed. So, and in conclusion, we could say one more thing. We should probably also say the company should not change its policy pricing. The company should not change its policy pricing. The order you do that in is up to you. You could have said something like, the company should not change its policy pricing because 77 lies within the interval. There doesn't appear to be enough evidence to say that the life expectancy has changed. All right, thank you for watching. I hope that helped.